Welcome to The Explainer. We've got a seriously urgent mission today. We are officially launching Mission Lorente, where we're going to learn how to measure the seemingly unmeasurable to map out critical environmental zones. Let's get right into it. 600.3, that's a massive number, right? We're talking 600.3 square kilometers, which is the sheer scale of our mission zone today. We're looking at the municipality of Lorente, way out in eastern Samar. It's this vast, historically rich landscape filled with really rugged terrain, sprawling mountains, and plains that face right into the Pacific Ocean. Because of this incredibly diverse geography, the folks living there rely heavily on farming and fishing. But here's the catch. This beautiful, resource-rich land is under threat. I want you to step directly into the shoes of a conservation planner today, because we have a huge task ahead of us. It's one that requires both strict mathematical precision and a genuine, deep care for the environment. So what's our actual objective here? Well, the Summer Island Biodiversity Project laid it out perfectly. They stated that livelihood projects should be integral components of the zone-specific comprehensive plans to protect each protection zone or how to restore restoration zones. The absolutely crucial point here is that we must create strict land use zoning. Why? Because the Samar Island Natural Park is facing severe, immediate threats from illegal small-scale logging, which has been directly linked to some pretty devastating floods and landslides in the area. We absolutely have to accurately map these protection and restoration zones to keep the land and its people safe. But this brings us to a huge logistical hurdle. How on earth do you measure a forest that has absolutely no straight lines? I mean, nature doesn't draw in perfect squares and rectangles, right? The rugged terrain of Lorente is wild and totally irregular. To solve this, we can't just rely on a standard ruler or simple standard measurements. Instead, we have to use grid maps and the mathematical art of area estimation. Section 1. The Art of Estimation. Think of a grid like a giant net cast right over the forest. Every single square unit within it represents a vital piece of protected land. To map it accurately, we follow 4 very strict rules. Step 1, count the fully filled squares. Step 2, if a square is more than half filled, we just go ahead and count it as one whole square. Step 3, we combine the exactly half-filled squares together. And step 4, we completely ignore squares that are less than half-filled. As you mentally mark these off, keep in mind that this mission requires extreme patience. A single miscount here means a major miscalculation in our conservation zone. Now, what's really interesting about this step is how visual it gets. Combining those exactly half-filled squares is honestly just like snapping puzzle pieces together. You're constantly looking for those geometric complements that, when joined, give you a complete picture. Or, in our specific case, a complete square unit of protected land. Building on that whole puzzle metaphor, 2 half-filled squares seamlessly combine to form one complete square unit. Whenever you spot these exact halves sitting on the borders of your drawn conservation zones, you just pair them up. 2 halves make a whole. It's a beautifully simple concept, but it's incredibly powerful when you're forced to estimate large, highly irregular areas. Okay, let's dive into this. Section 2, Mission 1 and 2, Triangles and Parallelograms. Imagine we've got a triangular restoration zone, or even a slanted parallelogram zone, plotted out on our grid. Neither of those is going to fit the square lines perfectly. For a triangle, we meticulously count the interior first. Let's say we find 6 fully filled whole squares. Next, we look at those slanted edges of the triangle zone, and we identify exactly 4 half squares. I want you to just pause for a second here, put that patience to the test, and mentally calculate the total estimated area of this triangle zone using the rules we just went over. You've got 6 whole squares and 4 half squares. So how many total square units did you find? If you calculated 8, you nailed it. We take our 6 whole squares and we add the 2 holes that we created by magically combining those 4 half squares together. 6 plus 2 equals 8. This right here perfectly demonstrates the methodical exactness we need for our map. Moving right along to Section 3, Mission 3, Breaking Down Trapezoids. When we're mapping out a place as wild as Lorente, we frequently encounter trapezoids, those 4-sided figures with only one pair of parallel sides. Think about the 2 methods we have. Method 1 is what we've been doing, meticulously, painfully counting full and partial grid squares. But Method 2 introduces a much more efficient breakdown technique. We can take complex shapes like trapezoids or those big slanted parallelograms and break them down into smaller standard shapes like rectangles and triangles. It's a real game changer for efficiency.
Let's visualize an isosceles trapezoid on our map for a second. Instead of counting every single square one by one, we can just draw straight vertical lines to split it perfectly into a central rectangle, flanked by two identical triangles on either side. Now we just read the grid to find our dimensions. Say the grid shows us that each of our two triangles has a base of 2 units and a height of 5 units, and that central rectangle has a length of 4 units and a width of 5 units.
So let's do the math together real quick. The area of a rectangle is length times width, so 4 times 5 is 20. The area of a triangle is 1/2 base times height. Half of 2 is 1 times 5 is 5. But remember, we have two identical triangles, so their combined area is 10. If the rectangle area is 20 and the two triangles are 10 together, what is the total area of this crucial restoration zone? 30. The total area is 30 square units. By calculating the 20 from the rectangle and the 10 from the triangles, we arrive at our answer so much faster. This proves that breaking complex shapes down yields highly accurate area estimations without having to squint and count every single partial square on the grid. All right, section 4, the big picture, preserving our land. So why does all this math actually matter? Because these exact calculations directly aid in protecting the 55 barangays located right in the core zone of the Summer Island Natural Park in Lorente. To do this accurately, you learned to identify full and partial grid squares. You learned how to combine halves like puzzle pieces. You discovered how to break complex trapezoids and parallelograms into smaller, totally manageable rectangles and triangles. Using precision in these mathematical estimations ensures that livelihood projects and conservation efforts hit exactly the right areas. Your patience in calculating is, quite literally, an act of care for the environment. So I'll leave you with this final thought as you step out of your role as a conservation planner today. How could your newfound precision impact and protect the natural world right around you? Math isn't just dry formulas on a page. It's a very real tool to understand, measure, and ultimately preserve the world we live in. Thanks so much for joining me on this explainer, and I really hope this leaves you inspired to see the real-world power of geometry in your own backyard.